And so the last section is that we're going to deal with over the next 2 days is on light and color. And actually, I have to, no, we'll do that later. Is on light and color. So just to kind of bring us through what we've seen in this unit so far, at the very beginning, we talked about the different things that can take place when light encounters an object, and what were the possibilities? Light is traveling along, it encounters an object. What can happen to that light? It can be absorbed, and that's exactly what we want to talk about when dealing with light and color, because that's what results in us seeing colors. Let's now review the other two. What else can happen? It can be reflected, it can bounce off, or, it can be transmitted through, and we just finished our section on transmission. That results in refraction, the bending of light. If we take a prism and we put nice curved surfaces on it, we can then get we can get lenses, and we just finished looking at uses of lenses. We looked at that old projector, and we looked at the magnifying glasses and all that type of stuff. So what we're talking about now in the next couple of days is what happens when light is absorbed by a substance, and very often certain colors are absorbed, or certain wavelengths we say, and that results in what we see as colors. Before we get to that, let's talk a little bit about 2 or 3 things here. First, I want you to define what dispersion is. And dispersion is when white light is separated into its colors. And I do want you to write down the colors of the rainbow in which they're dispersed. And so actually, I am going to get you to draw a little sketch here on the board. So once you've defined it, we're going to draw a little sketch of this so you can follow along and follow my picture. Sir Isaac Newton was the scientist who kind of came up with this theory to explain dispersion. Human beings had seen rainbows, well, as long as there's been human beings have seen rainbows. Sir Isaac Newton was the scientist who tried to explain what we were seeing. Sir Isaac Newton believed that light was made up of little tiny particles. Newton, by the way, Newton is the other guy in the hallway. I don't know if I've mentioned that. He's the other guy that's in the hallway other than Einstein. Newton was very much about forces and the way objects moved. So he imagined light as being made up of a bunch of tiny little particles. And he imagined that different colored light was made up of different sized particles. And that's actually not too bad. We now know that light is made up of waves. Remember, we talked about that at the beginning. They're electric field waves. And the different colors are different wavelengths, right? And we talked about that at the very beginning when we talked about the electromagnetic spectrum. We talked about radio waves and microwaves, and then ultimately infrared waves, and then we got to the colored light where we talked then about red, orange, yellow, green, blue, indigo, violet. So what I want you to draw is I just want you to draw a ray going in like this on an angle kind of up, all right? And that is a white light ray. So we'll say here that this is white light. And we already know, and I'm going to just draw a little tiny normal there. If this is glass or plastic, we're going to be going from fast to slow, and it'll bend towards the normal. And what happens is certain colors bend more than others. So the white light starts to spread out into its colors. Certain colors bend more than others. We saw that when we were doing total internal reflection. Remember how we saw a rainbow just before it disappeared? We're going to use this prism in a moment in our little activity also to produce a little rainbow, all right? So as it bends, it spreads, and when it comes back out, it bends away from the normal, and it spreads again. So it spreads out twice. And it turns out that the violet and the blue bend the most, and the red bends the least. All right? So Roy, O-Y-G, and I'm running out of room, B-I-V. Roy G. Biv. Do I have to write out what they all stand for? I'm assuming that's sarcasm back there. Red, orange, yellow, green, blue, indigo, and violet. All right? Now, Sir Isaac Newton saw this, came up with a theory. He was a little wrong, but it wasn't too bad. And he then hypothesized that if you could put all those colors of light back together again on the same spot, then you could reproduce the white light. And in the end, we call that, when we put it back together, we call that recombination. So please define recombination. And at this point, as you're writing, which is fine, I am going to, I need to do a little Alt-Tab here. I am going to pause my movie. Okay. I am going to start the recorder, but I am going to shut off the projector right now. So my voice will be on this. But what I want to do now is I want to show you what three colors we need in order to see white light. Now the other issue is we can't have too much light coming in from anywhere else. So Mitchell, if you could take that cardboard and move it up as if we were under lockdown here. And I'm going to shut this light off. We want it to be as dark as it can be in the classroom. I want this to be off. That's okay. We can. They're not that bad. They're not that bad. They're producing a little bit, but not enough that's going to affect us. Now the issue is when I fire up my projectors. All right. When I fire up my projectors, and oh, that's unfortunately low. Okay, I got a few textbooks here. Okay. And unfortunately, I also have a bunch of equipment sitting under here, so this is just a mess. That's what it is. All right, let's see if we can lift this guy up. I've got all these filters and things that I need to show you. So I wonder if I can get two of them propped up on one book. Oh, that was a success. Again, I'm fighting with all of these filters. I laid them out front so nicely when I left on Friday, and I didn't actually think about where I was going to project this. Can you see kind of there? Can you see kind of the screen that's happening here? So let's bring this one up like this. Hopefully I don't have anything fall off the back end. You catch that, it falls off the back end, okay? All right, so before we get going, here I've got a nice regular prism. And again, I can do the same little experiment that you guys just did. If I keep rotating that prism, I can get a fairly good beam of a rainbow there. There it is there. Hold on, it's right up there. Let's get it nice and tight. Right there. Right there, right straight up on the top of the ceiling. That's the same rainbow that you guys were seeing. And that has all the colors of the rainbow. Red, orange, yellow. The green is hard to see. There's a turquoise in there. And then there's a blue and a violet, etc., etc. Beautiful. Okay. So, the next way in which we can produce different colors is using filters. Now, filters, they work by absorbing the light. So this filter appears to be orange, and if I put the filter in front, it absorbs some of the light's colors. Now, that's the subtractive color theory. And I'm going to teach you more about the subtractive color theory after I'm done the additive color theory. But I do have to use the subtractive color theory in order to produce the colors that I want to see. So the way the filter works is, and I'm going to look here, this is a primary blue. The way the filter works is It absorbs all the other colors of the rainbow except blue. So, if this still works, I should be able to put my slide in here. How do I put that in again? I'm going to push this. Just jam it in. Oh, there we go. This has got to go in like this. It's got to go in like this. Oh, it would have been helpful if I'd practiced this. Right from this end. There we go. There we go. Beautiful. So, I've got the blue in the one on the left. Here I've got a primary green. That's primary green? That is BS. That is the worst primary green that I've ever seen. Let's try this primary green. That's better. That is a better primary green. So again, I'm going to try to load it into this one. Nope, it was in the front. So, primary green, excellent. So, you can see there a nice blue and a nice green. And what I'm going to do is now I'm going to add that light together. Now notice I'm adding light. I'm not adding together paint. Because if you've taken art and you've mixed this together, then you can talk primary color, right? And if you mix the paint together, you get another color. And how do people make an art of some sort? What are the primary colors when you're dealing with mixed paint? Do you remember? Does anybody know? That stage, remember? Is it red, blue, and green? That's for mixing light. That's not mixing paint. Okay. Is it red, blue, yellow? I'm not sure. Anyway, let's take a look at this. So notice here. Listen up. Notice here, I am not adding paint. I'm adding beams of light. I'm adding beams of light. So I'm going to add this green to this blue. And what do you think we're going to get? I'm going to take beams and I'm going to put them on top of each other. Any ideas? Yellow? Yellow is a prediction? Or orange? Yeah, orange. Why would you say orange? I would think we would need some other color in there. Let's put it together. All right. So what do we get? Yeah, we get a teal. We get kind of a light green. Now, in physics, the teal is actually called cyan. All right. So cyan is blue and green. I need one more color. Let's get these out of the way and get them separate. And I need one more. And unfortunately, my third projector does not have a nice folder, so I have to actually use my hand. And I want to put in front here red. Now, I'm going to add, this time, the red to the blue. Prediction? Purple? Yeah, we get a kind of a purple there. I wish the lenses weren't so dirty. Eh? Isn't that a mess? We got to get a pinky purple. We call this, in science, we call it magenta. I don't know why, that's what we use, magenta. Now notice, I put the red on the green a little bit. Did anybody see what the color was? It's a nice bright yellow. It's a nice bright yellow. All right, so that's kind of fun, all those colors. What if I mix all three together? Well, the rainbow would be a bit separate. What do you think? White light. Let's see if we can get all three together. Now, does that look white? No, how does it look? You don't know. It looks like a really, really faint yellow. Now, it is supposed to be white. It is supposed to be white. Now, the reason why it might not be white is that my filter might not be perfect. The filters might not be perfect red, green, and blue, all right? And or Some of these projector bulbs, one might be a little stronger than the other, and or there might be more dust on the lens of one than the other, and thus preventing the equal amount. But they should be white. Now, so what did we see here? We saw that we don't need all colors of the rainbow to get white, and I know that we had some people who might say that wasn't white, but again, these are just kind of old projectors. It's not exactly a perfect scenario, but we just need red, green, and blue in order to get white. So let's turn that on. Let's go on to the next slide here. All right, I'm going to minimize that. And again, we're going to be continuing to take some notes here. The additive color theory. Can we see the slide good enough there, Brett, behind that machinery? A little bit. I can unplug and move it to the side, and we'll bring it back out when we need it. And I started recording something. I would assume it would be audio, but I don't have my microphone in my pocket anymore. So I'm recording a part of the room. That's fun. I usually put it down by my computer. I don't see it. That's usually where I put it. Maybe it fell. Oh, here. It fell out sitting right there on that when I was reaching for something. Perfect. All right, I'll get this out of the way. We'll bring it back when we need it. Okay. So the additive color theory. When our eyes receive light energy, we see. This light energy can come from many sources, reflecting from a surface, transmission through a surface, straight from a light source. And that's what we want to talk about over today and tomorrow. How we perceive these different colors depending on how the light was originally formed, whether it came from a filter or whether it came from a white light source, all kinds of different ways. We just saw straight from a light source, okay? That was the light that came straight from that hot bulb. We actually saw also transmission through a substance because I put filters in front of the light source. So as it transmitted through, some of the light was removed. So we also saw transmission. And we did see reflection from a surface. When that light hit the screen, that light had to bounce back in order for us to see it. The reason it worked on that screen is because the screen is white. Actually, you know what? I don't know if you've ever noticed, that screen is not white. That screen is as old as can be. It's about a 25-year-old whiteboard. So that's probably also why that didn't look white, right, when we added the three beams together, because the screen itself is a little yellow. If I had a white screen, maybe we would be able to see it as white. I could test that in a minute, maybe with a piece of white paper. I could tape it to the board and we could fire it at the board instead. So that might have been why. When we get that fired back up, we'll test that in a minute. Okay, so next, and I don't know where I'm at. Am I at next? We see different colors when different combinations of light enter our eyes at the same time. It turns out that combinations of only 3 different colors of light are needed to produce all the colors of the rainbow in our eyes. It's very obvious when you're doing something. It's super obvious. So don't. On those computer screens or iPad screens or phone screens that some of us aren't supposed to be looking at, there's actually only 3 different colored pixels on that screen: red, green, and blue. And by the computer program varying the amounts of red, green, and blue that come from a single space, because they put them super together, like really close together, by changing the amounts of red, green, and blue, they can produce all of the colors that you would ever be able to see with the way our eyes function. Yep?
How do the applications project those colors?
What do you mean? Oh,
When you open up an application.
it's part of the programming, right? So it wouldn't be, they wouldn't have to program every little pixel, right? Because of the way computer programming has kind of developed, there would be all kinds of these sub-programs that would be built into the hardware and the software of the phone itself or the device, that then the app programmer just needs to tell it what color it wants. The programmer, the app programmer, doesn't have to actually program each pixel. So if he tells an area to be blue, then that lower level of programming is going to dictate where to put the colors and how to run the pixels and that type of thing. So there's multiple levels of programming that work that way. But at some point in time, the designer must develop the hardware, and then somebody's got to write some code for each one of those little pixels. All right, and then the higher level programmers will use that feature, and it'll just tell it what to do, right? So there is different levels of programming. But somebody at some point's got to tell every one of those pixels which color to become. All right. So when I type on here, the word produce, I don't have to program the projector to put a white P there. I just have to use Microsoft PowerPoint, which someone else did a level of programming. The PowerPoint people didn't do it. The video driver, you know how there's a driver in each of these things, the driver has got to tell the monitor what to do, right? So it would be the lower level of the drivers that would be probably telling it what to do. And your phone would have drivers as well, okay? Okay, good question. So again, it's only those 3 colors that are existing in this device, in your device, et cetera, et cetera. So how do we get all of the colors? We put them together as the additive color theory, and you can draw this, write it down just as 3 concentric circles. So in your note, put additive color theory, put 3 circles that are overlapping, like a Venn diagram or whatever they call those things. I don't ever use Venn diagrams, but make them fairly big. And we will label all of the colors that we need in order to add them. Now, again, I want to stress to you that all of the colors of the rainbow can be obtained by having various combinations or brightnesses of each of these colors. And again, the programmer tells how bright it's going to be. That gets you an orange, or it gets you a fuchsia, or I don't know, some odd color, something that is a mauve. I don't know. You know what I mean? But we're only going to deal with just the main colors. Yep.
Question.
Yep.
When you take a already pre-programmed picture,
Yep.
and you zoom it in and you see the tiny little pixel,
Yep.
how is it projecting different pixels for that one pixel?
I'm not exactly sure of the question again. I want you to ask it one more time.
When you zoom in on a picture, you get...
You mean zoom in on a pre-existing picture, like an old picture that had less pixels?
Yeah. Okay,
gotcha.
And you zoom in.
And you zoom in, what tells that array of pixels to be that one pixel? It would be, again, in part of the programming. You can't have more detail than what you originally took the picture with, right? So as you zoom in, the computer is then losing the ability to get the fine structure of the picture, right? Because it doesn't exist, because it was a lower resolution picture. So again, somewhere in the programming, what the driver is then saying is, I can't distinguish any more of those colors. So I'm going to have this whole big block as being the same color. You know what I mean? So it's the driver that's trying to interpret the lower resolution image. It's a programmer, again, that has said, well, if the data isn't there, what you got to do is you got to just make a big area to be that one picture, right? And then if we squeeze those areas down, then you can see it looks more like an image. But when you zoom in, you lose that. You lose that. So it's got to be just a programmer again. Could they smoothen it out? Maybe nowadays there's even more ways to make it smoother, but you still can't create more data out of the data that isn't there. Okay, 3 concentric circles. Again, let's just put here G. Do we know what G stands for? We're okay with G? All right. Green. Let's go with R. And let's go with B. Those 3 colors are what we call the primary colors using the additive color theory. Again, if you've taken art and you've mixed paints, they would have a different group of primary colors. But from my question before, this doesn't affect us because you guys can't remember what the primary colors were in art anyway, so it doesn't matter. Did you? Oh, okay. All right. Red plus blue gets me this purpley color, but what did we call it? Magenta. 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 And you can see that it's kind of purpley. So blue and red makes good sense. Red and green makes yellow. That's pretty straightforward. That's a tough one to remember. I struggle to remember that one because I always think that it should be more orangey, but I guess you can imagine that red, orange, yellow. Yeah, that's not bad. So green and red make yellow. So let's do the last one here. Blue and green make cyan, teal. It's cyan is the term we use. We'll write them out in a moment. And if we, and by the way, magenta, yellow, and cyan, we call them the secondary colors. The secondary colors come from the addition of 2 primary colors. And the last one here is white. And that actually looks more whiter than the last one, so when we did actually put it together. So that is white. All right, excellent. Let's define some of these things. So please write that down. Please write down what these, so let's define them. So on our test on Thursday, when we go over the review, remember last test, I let you have a little piece of paper that had the rules for the ray diagrams. Again, when we do our ray diagrams for lenses, I'm going to let you have a piece of paper with the rules for the ray diagrams, but I'm also going to let you write on there that color combination diagram so that you don't have to necessarily memorize those colors. You'll have them on a diagram for the test. Okay, so I'm going to let you have a little more for this test. Red, green, and blue, they're primary colors. Primary colors, they add up to white. Secondary colors, yellow, cyan, and magenta. And they are the colors that are formed when you add 2 primary colors. What's that? Yep. Oh, okay. Yep, I do watch television. And it will have the same red, green, and blue pixels on it. The greater the definition, right? So right now, my TV is just an HD TV, high definition, but now there's 4K. That just means that those pixels are getting smaller and smaller. They have the ability to produce that red, green, blue in a smaller and smaller area, so they can put more pixels on the screen, and therefore you've got that sharpness, right? The more pixels you have, the sharper the image is. But each one of those pixels has the ability to produce red, green, and blue. they're getting to the point where they can produce light using something called a quantum dot. And that is almost the smallest way in which they can produce a little flash of light. It's almost getting on atomic scales where the atom is simply producing that little bit of light. So they're getting to the point where there's going to be an extreme. They're not going to be able to increase the definition over and over again. There will be an extreme to the size in which they can make those pixels small, because they will become on the size of atoms, and then they're going to run out of space. You can't produce light without atoms. You need those electron jumps that we talked about. You can't just have something smaller than that produce light. That's the fundamental limit to that. So there will be a limit to how much definition there is. Yep. Splitting them into what? Half atoms? Didn't we do chemistry? Half atoms? Your brain should be screaming, not possible. You can take a uranium atom and split it into two atoms. You then get two smaller atoms. But you can't get anything smaller than the atom itself. You can get particles that are smaller than atoms, but they're not atoms anymore, and they don't have the ability to produce light, because atoms have the proper mechanical parts that allow the light to be produced. So you could produce particles that are smaller than atoms, but they're not light-producing particles. I guess you could accelerate one, but then you've got moving particles. That wouldn't be useful for a screen. Anyway, all right. Complementary colors. Interesting path that we've gone down here with half atoms. Thanks, Pat. That's good. Complementary colors, two colors that can be added to produce white light, and they are always diagonal from each other on the chart. So if I have here yellow, there's the yellow. Remember, yellow is already made up of red and green. So what else needs to be added to that to make white? If I have yellow, which is already made up of red and green, you can see it there. There's the red, there's the green. So yellow already contains two of our main three. What other color will add to that to make white? Blue. So I need to add blue to yellow to make white, because the yellow already contains the red and the green. All right? Okay? Notice that the yellow and the blue are on opposite sides from each other. So, red. Red only contains red. What other single color would I have to add to that to get white? What do you think? Cyan. It's on the other side. So I'd need to add cyan to that, because in the end, I need red, green, and blue. Does it make sense? So they're kind of opposite each other on that diagram. Magenta. What would I add to magenta in order to get white? I would add green to magenta. It's opposite of magenta. There's magenta right there, and I would need green. Okay? All right. So they would be called complementary colors. Now, that's the end of my little note on additive color theory. I'm going to continue on and talk about the subtractive color theory right now, even though it's the next day's lesson, because I'm not going to be able to finish it in today's lesson, but I'm going to have it extend over into tomorrow's. Then tomorrow, when we're done early, we'll watch a video, and then I might start it on the review tomorrow at the end of class. Yep. Yeah, subtractive color theory, there's also notes. What I'm doing at this point is I'm not going to just show them kind of a half video, because it really doesn't make much sense to do that, because my video is 50 minutes. So I'm going to just keep going, and whenever we get done tomorrow, we'll be done our notes, and then we'll get ready to review. So discard that. We're going to get rid of, I just opened the additive color theory. I need to open the subtractive color theory. Subtractive color theory. And you can put that title down, subtractive color theory. And this next slide, for those maybe who found it on the thing, the next slide, don't write that down. Don't write that down because we already talked about that. So just write down the subtractive color theory. I will talk about the next slide, but then we will move on to that from there. So it says there, when light reflects off of a surface, so this is caused by reflecting, so you'll notice my lab coat, the light comes in, hits my lab coat, goes into your eyes. So when light is reflected off of a surface, like my coat, or transmitted through a substance, like this filter, so as it goes through, some of that light can be absorbed, all right? There are chemicals in here that have the ability to absorb some of the light. Same with the dyes in my coat. There are chemicals in these dyes that when they strike the coat, some of the light is absorbed, but the red light is not absorbed. So what we see is actually what is not absorbed. Every other color is absorbed. There are two ways in which we can do this, and I do want you to, do I want you to write this down? I do want you to write this down. But we will eventually be going to a handout, all right? And the handout then will contain a bunch of these pictures. We won't have to draw them all. What do we got?
I need Logan and Tyson, please.
We're going to Tyson. And I'm just going to check something here before we go too far. I'm going to freeze that because I'm wondering if we can then go to our handout at this point. Yeah, I want you to draw that first one there. And then I'm going to check something on my Google Classroom here. Okay, and actually, once you're finished drawing that one, open up the document that I've given you on Google Classroom, because that document contains multiple pictures like this so that you don't have to draw it over and over again. All right? So we're going to use this one the way it is, and then we're going to open up the document on Google Classroom, and then you can fill in what we're writing without having to draw that over and over again, because that's kind of a pain. Okay? It appears blank. So blank colored light was subtracted. And again, if you go to Google Classroom, and I'm going to show you what that looks like right now. So I went to the subtractive color theory. I opened that document up. And in the subtractive color theory, oh, you can't see any of that because it's frozen, which just kind of defeated the purpose. So what I did was I went to Google Classroom. I opened that document, the subtractive color theory, and in there you can see there's many, many of these pictures. So if you then click on the right, the button where you can write on it, you can then fill it in. Does that make sense? Save you having to draw this over and over again. Are we okay with that? It's all right. So you could start with this picture here if you wanted to. I know I made you draw it out. If you want to put the one in your notes, that's fine. Or you can zoom into that one and you can draw that one. What I've got here is this box here in the corner describes what color the filter is, okay? And then I've got red, green, and blue light, and then I've got that statement, it appears blank because blank was removed, because we're removing light, and we want to talk about how it's being removed. We do have some blanks up top. When light blanks off a blank or is blank through a blank, does anybody have any ideas on what I want there? That came from the start of the note. Yep. When light reflects off a object or surface or is transmitted through a substance. Substance is fine, through a substance. Some of the blank colors of light can be removed or subtracted because we're subtracting the light away. Don't worry so much about that. We can get that filled in. So I'm going to switch back to the PowerPoint because the PowerPoint is big and it's easier for you to see what I'm doing here. So right now, you're hopefully zoomed into one of those squares and you're ready to fill it in. Is that true? Is that what we're looking at? Nice. Are we zoomed into one of those? Excellent. Good job. You can write there colorless filter in the box. Now, I don't have a colorless filter because that's kind of silly, but I do have this piece of plastic that holds my slides, and I guess you could say that's a colorless filter. So if I were to shine red, green, and blue light at that colorless filter, what would go through? White, which means which of the colors made it through? All of them. So here's how we're going to answer these questions. You need to keep your color circle in mind. So you need to keep that nearby. And I'll draw one on the board so I don't have to write it in all the time. Red, blue, green, yellow, cyan, magenta, white. So if a colorless filter had white light shine upon it, in our eye, it's going to appear white. It appears white. So which colors have been subtracted if it appears white? Careful. None of them. Which means I can do this visually and help me think it through by putting all the colors through. If all the colors hit my eye, then it appears white. Make sense? Let's now pick a different colored filter. So you can slide over to the next box. And this time we're going to analyze a red filter. Well, if I have a red filter, here I've got one right here, and if I shone white light through that red filter, how does it appear to your eye? Red. It's really simple. This is an obvious one. It appears red. So if red was the only one to get to our eye, what had to happen to the other colors? They got stopped. They were absorbed. So it appears red because blank and blank colored light were subtracted. I don't know what space you have there. You have, because blank was absorbed, so you're going to have to put two colors in there. What two colors were absorbed? Green and blue. So again, you can imagine almost like the color wheel is coming through the filter. That color wheel is coming through the filter. The only one that can get through is what you see. It's red that got through. Let's do another one. A green filter. I'm hoping this is becoming obvious, maybe?
Green.
Green filter. It appears green. This is the type of thing that you might be able to finish yourself without my assistance. What is absorbed? Cade, you're going to resist the drive to answer. Hands up, and I'm going to pick on certain people. Oh, what's absorbed? Red and blue was absorbed. Red and blue. I'm checking to see that others are following along. Make sense? All right. What's my next one? Blue. Well, you think I was that obvious? All right. Again, I'm hoping you can complete that without my assistance. I do have a blue filter right there. Blue filter. Blue, it appears blue, and so red and green were absorbed. Okay? What's my next one going to be? A cyan filter. Now your spaces all look the same, so you've got to kind of squeeze in there. Well, if it's a cyan filter, it's going to appear cyan. But we want to, I don't even have a cyan filter nearby, do I? Oh, there is one right there. It's going to appear cyan. But I only have red, green, and blue being fired at it. So what two colors had to hit my eye in order for my eye to perceive cyan? What two colors have to strike my eye in order to perceive cyan? Jake? So I need blue and green to come through. Blue and green. So because I still use the additive color theory, even though we're subtracting light away, I use the additive color theory to tell me what passed through. So it appears cyan, that's obvious, but cyan is blue and green. So what color had to be subtracted from that one? Yep, red. So red was absorbed by this cyan filter, the thing that was grabbed up. Okay? Red. All right? I'm kind of jumping ahead, but this is not a bad thing. We haven't talked about reflection yet, but during the summer, leaves are, they're green. Thank you. Thank you very much. Leaves are green. If they've reflected green, what colors had to have been absorbed? And red and blue. Now, we all know that plants produce food through photosynthesis. You heard that before? And it turns out that the color of light that the plant needs is not just regular light, but it's the red. It's the red because it's absorbing the red. It's reflecting the green back out, which means it's not using the green. It's absorbing the red and some of the blue. The cells that absorb the red are in there absorbing red. And then when the plant's leaves die, the chlorophyll, the green part, dies and disappears, but the part that used to be absorbing the red is now reflecting the red because it's dead too. And then in the fall, the leaves appear red, orange, etc., because that light is now being reflected back. So there again, that's kind of a use of that. Yep?
What happens when we get a calm state of
Ah, well, what if I had a black filter? What if I had a black filter? What's that? You don't see anything. What light made it through? Nothing. So black is the absence of any of the light. Yellow filter. What's getting through on a yellow filter? What's getting through on a yellow filter? Which one are you doing there, Jacqueline? You're just fixing it up? Can you get to the yellow filter? I want to see if you can see how this functions. So here I've got a yellow filter. She's filling in yellow as we speak. As I speak. Okay, now up to here. In order to have the yellow come through, what colors came through there? Which two colors get to come through that allow us to perceive yellow? I need two of these colors of red, green, and blue. Which two will allow me to see yellow? Of red, green, and blue, which two? Red and green. So, red and green get to go through. Red and green. Because those two make yellow. And that's why we picked red and green. So it appears yellow, which is red and green. Therefore, which one was absorbed? Which one was absorbed? Yep, blue. Blue was absorbed. Blue. How many more of these have I got? When do I get to the pigments? Magenta filter. Oh, that's fun. Do I have any pictures with the two filters back to back? Let's jump ahead to the two filters back to back. What have I got here? Blue and red? Where's my blue and red filters? All right. Blue and red filters. These are not perfect blue. I don't like this blue. I like this blue. Oh, there it is. I like that blue. And I like that red. What's going to happen? Let's treat the filters one at a time. What does a blue filter let through? Yep. It's got to appear. So it appears blue, right? So let's say I've got red, green, and blue coming through here. Which one is able to go through? Blue. Blue. Blue goes through. Blue goes through because green and red are absorbed. Now, red normally lets what color through? Red. But is there any red light left? No red light left. The red light is stopped there. The green light is stopped there. The red filter is stopping the blue. So there's no light. If there's no light, how should it appear? Black. Black. Therefore, it is black. Now, normally I like to do this with projectors. We can stop there. You guys can close your stuff up. But normally I like to do this with projectors, but let's see if it works here. If not, I'll plug in the projector. Can you see the red and the blue? Yeah. All right? What's it look like? Black. Does it look black? Yeah. All right? Let me show you one other interesting thing. And we'll write this down tomorrow kind of as a review. What does yellow let through? What does yellow let through? It lets through green and red, right? Green and red. How does it look? It looks red. Doesn't matter which way I do it. Looks red. Now here, watch this one. Yellow and blue. What does yellow let through? What does yellow stop? Yellow stops blue. So if I put a blue in front of the yellow, how is it going to appear? Somebody said it. Oh, that's fun. There's a little cyan in there. It's supposed to be black. It's supposed to be black. The reason this isn't black, one of these aren't a perfect yellow or one of them isn't a perfect blue, right? If we had perfect, it should have stopped it completely. If I don't have such a bright light behind it, I could sell it to you that it was black, right? I could convince you that that was black. But when I put a super bright light behind it, there is a little bit of something there. It's kind of a gray. Okay, so we can pack stuff up. Tomorrow we're going to finish off this discussion. It won't take the full period. We will watch a video about color, and then I might start in on the review so we got a little more time to review the next day. Like, you know how I write down all that stuff on the review? We might start in on that tomorrow. 5%, I'll charge that up. Thanks.